Hello, this is Jake Abbott. In this video, we're going to be talking about the actual time domain solution of state space equations that are linear time invariant state space equations. So let's remind ourselves what those are. We're talking about linear time invariant state space equations that look like this form, where we have some x vector dot is equal to ax plus bu, and I'm explicitly indicating that these signals x, u, and y are all vectors, and that they're varying in time, and the matrices A, B, C, and D are not varying in time. That's what makes an LTI system. And we want to solve this equation. So these differential equations ultimately describe the relationship that the equations have with one another. And the x dot equations, you can say if the states are all the important piece of information, x dot describes how those states evolve as a function of the current state values and the current input values. But we actually want an equation. We want something that looks like x of t equals something. What is x of t? This is what we're going to be interested in, and we want to solve that from these equations. We also are interested in y of t, but it's pretty obvious from this bottom equation that once we know x of t, and since we explicitly know of u of t because we're the ones controlling it, once we know x and u, it's really easy to solve for y by just multiplying them by c and d. So solving for y isn't really the interesting part. It's solving for x that's the interesting part. So how do we take these differential equations here, this big differential equation, x dot equals ax plus bu, and solve that for x? And to solve that for x, I mean, really we're going to say we want to solve x of t equals something given some u of t. So I'm going to control some u of t that's evolving in time. And then I also need to know what my initial state is. So what is my state at time 0? And knowing those two pieces of information and knowing this big differential equation, I should be able to solve for x of t and how x of t evolves for all time. So there's one little linear algebra trick that we need that was, I think, covered in the Jordan form video. And it's this trick. If we have this e to the at, and remember a is an n by n square matrix, and I take the time derivative of this matrix, and this was done using series expansion, you get that this thing is equal to e to the at, and it's also equal to e to the at times a. So what we want to do is we want to go back up to our main state space equations, and we want to pre-multiply both sides by e to the minus at. I'm also going to bring this ax over to the left side, so I'm going to skip a step here just so I don't have to write so much. So I'm pre-multiplying everything by e to the minus at, x dot of t, and then I've brought the ax over and I'm pre-multiplying, so here's e to the minus at ax, and then that's equal to e to the minus at times b u of t. So I just skipped one step. I brought this over to the left side, and then I pre-multiplied the entire thing by e to the minus at. And if I do that, I can look at this term here, and I can recognize this is actually d dt of the quantity e to the minus at x of t by the chain rule. So if you do this by the chain rule, you first derivative of the first times the second plus the second times the derivative of the first, and since they're matrix vector equations, you can't change the order around, and that gives you this. And so I basically have this d dt equation is equal to this equation. And then I can integrate both sides from 0 to t, where t now is explicitly the instant in time that we're interested in looking at. I mean, we're ultimately trying to get this equation x at t, at any instant t. So I'm going to integrate both sides of this equation, both the left side and the right side, to get rid of this d dt, and I'm going to integrate it from 0 to t. And so that's going to give me something that looks like e to the minus a tau, and tau is just going to be my dummy variable of integration, x of tau, evaluated at t and tau equals 0 is going to equal the integral from 0 to t of e to the minus a tau b u at tau d tau. So if you don't remember how this calculus works, remember that tau is just a dummy variable, and if you take the integral of a derivative of some function f, what you really do is you just evaluate that function f at the two limits of the integration. So this had a ddt in front of it. By integrating, you get rid of the ddt, and then you evaluate this thing at those two extremes. That's how you do an integral like that. Okay, and if we substitute that in, what we get is e to the minus a t x of t minus e to the 0 x at 0 equals, this side is unchanged, e to the minus a tau b u at tau d tau. Okay, so now we need to acknowledge that this e to the 0 is the identity matrix, which we've shown before. And now what I'm going to do is I'm going to pre-multiply both sides of this by e to the at. So let's do that. So I'm going to put in e to the at here, and I'm going to put in, I'll just put a minus sign, e to the at there, and then an e to the at there. Then I acknowledge, okay, this is just an identity matrix now, and this identity matrix times e to the at, it's just like it doesn't even exist, doesn't do anything. And then the next thing I want to sort of notice is this thing here, e to the at, it's not a function of tau. So as far as this integral is concerned, which is integrating over tau, it's just like a constant. So it stays completely separate from the integral. So I do a little simplification here, and I get that x at t is equal to e to the at x at 0 plus the integral. So I'm moving this e to the at inside, but it doesn't have a tau in it at all. So I have this e to the at e to the minus a tau b u at tau d tau. And then the last thing I do is I bring these two terms together. So I have x of t is equal to e to the at x at 0 plus the integral from 0 to t of e to the a t minus tau b u at tau d tau. Okay, I'm done. This is the solution for x of t. I look at this and I have x of t equals, and it's some function of time that needs to know my x naught value, and it needs to know my u of t all through time from 0 up until the current time that I'm interested in. And that makes sense. I mean, as x evolves, it sort of holds on to all of the u's in the past through time. And if you think about that, you can see that this x naught is evolving in time by this e to the at matrix. And so as time goes on, the effects of this, maybe they're decaying away, maybe they're growing, maybe they're staying the same, and it's all going to be a function of this e to the at matrix. Then I sort of see the same kind of effect with u. I need to know all of the u's that existed from time 0 up until the time we're interested in t, and those u's come through the B matrix, which is seen right in our original state space equation. But then once they enter in, those effects of u are also decaying away, and you can see that it's the difference between the time that you're integrating, which is tau, and the current time of interest. As those become very big, maybe they've decayed away a lot, or if you have an unstable system, potentially maybe they're growing a lot. And so this is sort of accounting for the fact that past inputs have different effects on the current state value. So this here is the general solution for x of t. It isn't super clean, but it can easily be solved numerically. But analytically, this right side, everything to do with u, is just a little a little unsatisfying how complicated it is. If we don't consider the inputs at all, then the solution for x of t is really simple, and that actually is something we can really easily wrap our heads around, like this. Just if I take a system with some initial state and I don't give it any input, so this is the zero input response of the system, then that's something that's very easy to analyze, and it's really this e to the at matrix is very important. So one thing that we should note for this general solution here, it is very easy to sort of prove to yourself if you analyze this equation at t equals 0, then what you get is you will get that x at t is equal to your initial condition. So you can sort of prove to yourself quickly that this works for at least that one data point. This whole complicated equation will collapse down to just this value. So we also have this equation, right? Y of t is equal to c x of t plus d u of t. So now that we know what x of t is, and we already knew what u of t was, it's really easy to solve for y by just pre-multiplying the x terms by c. So take that huge equation we just had and multiply everything by a c on the left, and then add a du on it, and then that's your general equation for y of t. I'm not going to bother writing all of that stuff down. So we saw in the last slide that the solution for x of t very heavily relied on this e to the at. Now you can go back to the video on Jordan forms, and we spent a lot of time looking explicitly at what this kind of matrix looked like. So we already know a lot about that flavor of matrix that's going to be so important in these state space equations. So I'm going to write this out one more time so we can talk about it a little more. So x of t in general, and this is something that you're going to want to memorize, is equal to e to the at times x naught. This is by far the most important part of the equation. And then it also equals the integral from 0 to t of e to the a t minus tau b u of tau d tau. So this is the general equation, and we call this here the natural response of our system. And most of you will have seen these sort of dynamic system equation terminologies before. The natural response of our system is the response if we don't do anything to it. Basically, we give it no input, and we just have some initial condition, and we just watch our system evolve from that initial condition. You can't say it's based on anything but itself, because you're not doing anything to it. You're setting u equals 0, and you're just watching your system evolve. And then we call this term here the forced response. And it's highly dependent on what u we're giving it. If we give a sinusoidal u, usually we see sinusoidal type forced responses. If we give step inputs in u, we see sort of step input forced responses. Those are kind of typical behaviors. But the complete response, x of t, is going to be the summation of the natural response and the forced response. So we're going to be, for a while here, we want to talk about the natural response of systems. The forced response, like I said, if you're giving inputs that have a certain shape, then the forced responses tend to kind of be of that shape. The natural response of a system ultimately tells you if that system is kind of a first order, kind of damped response, if it's a second order kind of oscillatory response, if it's a stable system, if it's an unstable system. The natural response of your system is going to tell you all of this stuff. So that's what we're going to focus on for a little while. So let's do an example. And let's consider a really simple equation where our x vector is an R1 vector, meaning it's just a real number. It's not a vector at all, it's just a scalar. And our A matrix in this case is just a little scalar A. So if we do this, then our general solution for our vector x of t becomes this scalar solution, e to the at x naught. And I want to do that because you should have all seen this sort of response before. And we're going to use our existing knowledge about this type of systems to sort of ground us in what we expect to see. So I want to, here's a plot versus time. And what I want to plot is let's say this is our x naught. Let's look at what this equation looks like for different values of a. So if a is less than 0, if a is a negative number, we sort of see this first order damped response where this is asymptotically going to 0. So this is a less than 0. So this is a response that we typically call a stable response. If x of 0 is just some number, it's just going to decay away to 0. And we can describe that decay with time constants. If a is equal to 0, things just don't change. And you can see that by looking at e to the at. If a is 0, then that's just e to the 0, which equals 1. And so x of t is just equal to x naught all of the time. And then if a is greater than 0, we see an unstable response where x of t is just going to grow to infinity. So this is a type of response that we've seen before. Now, let's consider another example. And in this example, we're in a vector space now where x belongs to R2. So now we have a 2 by 1 vector x, and let's consider the case where our A is a diagonal matrix. And let's say it has two distinct eigenvalues, lambda 1 and lambda 2. So if we look at our solution for this equation, it looks like x1 of t here and x2 of t. I'm just still using the general solution from the previous slides. And this looks like e to the lambda 1t, 0, and e to the lambda 2t, 0, times x1 naught and x2 naught. So when I look at this and do this actual multiplication, I get that x1t is equal to e to the lambda 1t, x1 naught, and I get that x2t is equal to e to the lambda 2t, x2 naught. So these two equations are completely decoupled from each other. x2 doesn't affect x1 and x1 doesn't affect x2. And each one of those decoupled variables looks just like the scalar first order variable from the previous example. So because they're decoupled, if one is unstable or one is stable or one is marginally stable, meaning it's not growing or decaying, it doesn't affect the other one. But if you think about that this x vector is equal to x1 of t and x2 of t, it only takes one of these being unstable and the whole vector as a whole goes unstable. Like let's say this goes to infinity. Who cares if this goes to 0? The vector itself is going to grow to infinity because one of its terms are growing to infinity. So to kind of summarize what that means in that case, we can say if both lambda 1 and lambda 2 are less than 0, then our x vector goes to the 0 vector as time goes to infinity. So basically, both of them are stable, they're both decaying away to 0, and then x, which just is the combination of the two, it's also decaying away to 0. So if either lambda 1 or lambda 2 is greater than 0, and of course if both are greater than 0, it's the same thing, but only one needs to be greater than 0, then x of t goes to infinity as time goes to infinity. And then if lambda 1 equals 0 and lambda 2 is less than or equal to 0, and it doesn't, this order doesn't really matter, so I'll just say or vice versa, then x of t goes to some constant vector. And all this is basically saying is, neither of them are greater than 0, so it's not growing to infinity, and at least one of them isn't decaying away so at least one of them is equal to 0. If they're both less than 0, then we're back up to this first case. So at least one of them needs to be 0, but they could both be 0. That's all it's saying. In that case, then this x of t goes to a constant vector. So let's consider another example. In this case, it looks a lot like the last case. So let's consider x belongs to R2, and now A equals still a diagonal matrix, but instead of having two different eigenvalues, let's say they're the same. So it's got one eigenvalue with multiplicity 2, but it does have two eigenvectors. And the reason why we know that is because this A matrix has two Jordan blocks in it, and each Jordan block has an eigenvector associated with it. So this matrix will have two eigenvectors, and the solution looks exactly like the solution from the last case. So we have x1 of t and x2 of t equal e to the lambda 1t, 0, 0, e to the lambda 1t, x1 naught, x2 naught. This is just exactly like the last one, and there's still two completely decoupled equations. The equation for x1 of t has nothing to do with the equation for x2 of t. The only difference is they have the same eigenvalue, so they're sort of evolving at roughly kind of the same rate, but they're still completely decoupled from each other. Nothing much has changed. So now let's do an example, though, where things are getting a little more interesting. So let's consider x belongs to R2. We're leaving that the same. And let's say A has this sort of form. Lambda 0, lambda 1. So now it's still has one eigenvalue with multiplicity 2, but this is a Jordan block, a 2 by 2 Jordan block. So rather than the A matrix being composed of two 1 by 1 Jordan blocks, each of which has its own eigenvector, this A matrix only has one big Jordan block, and since it only has one Jordan block, it only has one eigenvector. So how does this solution look? So the general solution that we derived earlier in this video still holds. So I'm going to have x1 of t and x2 of t equals, and then what is e to the at for a Jordan block? We solved that in the Jordan form video, and that looks like this. It looks like e to the lambda t here, e to the lambda t here, a 0 here, and then this looks like a t, e to the lambda t. And then I'm going to times that by my initial condition vector. And when I look at this, my equation for x2 of t looks just like the equation for x2 of t did last time. Nothing different. And you see it doesn't have an x1 in there at all. It's completely decoupled from x1. But if I look at how x1 of t looks, I have e to the lambda t, x1 of 0. That looks like the one from the last example, but now I have this new term, t e to the lambda t times x2 at 0. So while the equation for x2 of t is fully decoupled from x1, meaning that x1 doesn't influence it at all, x1 isn't really decoupled from x2 because my initial condition of x2 does appear in x1. And it's only the initial condition of x2, not x2 of time. So x2 of time starts evolving, and maybe it's stable and it decays away, or maybe it's not, depending on this eigenvalue. But no matter how it evolves, x1 doesn't know that. All x1 can see is what value it had at the beginning. And it's got this weird term here, t e to the minus lambda t, or not minus lambda t, t e to the lambda t. And so what does that function look like? Let's plot that. Here's time. Let's plot t e to the lambda t. Now if lambda is less than 0, you get something that looks like this. So this is lambda less than 0. So you have this thing where at the beginning of time, it actually starts to grow. So when time is very small, the time term here dominates over the e to the minus, or e to the lambda t, and it actually grows. But after some amount of t, this thing starts going to 0 so fast that even though time is still growing, e to the lambda t is shrinking faster than time is growing, and the multiplication of those two goes to 0, and eventually this just decays away. Now if lambda is equal to 0, then t e to the lambda t becomes t e to the 0, which is just t. So that's just a perfectly straight line. Like this. So that's lambda equals 0. And for lambda greater than 0, I have this very growing to infinity thing happening. So this is the function t e to the lambda t. And so as long as lambda is less than 0, then you're totally fine. Whatever this initial condition on x2 is, this whole term here will eventually decay away to 0 like this. But if lambda is equal to 0 or greater than 0, then that initial condition on x2 is just going to cause this term to just grow and grow and grow throughout time. So for an equation like this, it's not good enough that we have our lambdas be either less than or equal to 0. They actually need to be less than 0. So, and this is something that just falls out of this Jordan form, and it's all based on this one term here. So the lesson from this is that an A matrix of lambda 1, lambda 0 is very different in its time response from lambda 0, 0. And it's because of this other term. So we're going to see this repeated over and over throughout this semester. So the concepts we're talking about, I've been talking about R2. But the concepts we're talking about here are for general R to the n, for n larger than 2. They're true for just general vectors. Some of the things that are important here, we've talked about changes of basis. We've done similarity transformations when matrices are diagonalizable, and also when they're not diagonalizable, but they're still similar to a Jordan form matrix. So we have this idea that through some similarity transformation, I can find some new x tilde, which is equal to p times my original x, where p is just some equivalence transformation. So it's some n by n real non-singular invertible matrix. So P inverse always exists. And I can do some transformation like this, and we've spent some time talking about this sort of thing. And just only looking at this, so we know this sort of thing exists, where P is a square matrix, P inverse exists, so we can also write P inverse times x tilde equals x. But just from looking just at this equation alone, I mean, this is just a matrix. This is just an n by n matrix that I'm multiplying x by. So if I know that this x vector is going to 0, then I also know that x tilde is going to 0. Because if I multiply p by a 0 vector, I get a 0 vector. The same thing goes for infinity. If I know that my x vector is growing to infinity, if x is getting huge and then I multiply that by some matrix, then my x tilde is also going to grow to infinity. So what else do I know about this? I know if I take the derivative of both of these sides, I get that x tilde dot is equal to p x dot. And I can also invert this, and I can put dots on these like that just as well. So if I have my initial equations, x dot is equal to ax plus bu, and I substitute in for this. So let's use this equation right here and substitute that in. I get p inverse x tilde dot is equal to a, and then I'm going to substitute in that original equation before I put the dots on it in for x here. And so I get P inverse x tilde plus BU. And then I multiply by P on everything. I get x tilde dot equals P inverse x tilde plus P B U. And this matrix here, P inverse, is just a new A matrix for this system. I'll call it A tilde. And this PB is just a new B matrix. I'll just call that B tilde. And then I can carry through the same sort of substitutions, and I can write Y now as C P inverse X plus du. And so this, I can call this new thing a new C tilde, and then D and D tilde are just the exact same thing. So I can do this substitution, and when I'm done, I have a new set of equations where A is similar to A tilde. And what does it mean that A and A tilde are similar from each other? Well, if we remember, it means they have the same eigenvalues. It means they have the same characteristic equation. And what that really means is the time response, the fundamental time response, isn't changing. And it all comes back to this idea here. It means that if x is going to 0, then so is x tilde. And if x is growing to infinity, so is x tilde. So the fundamental stability properties don't change through similarity transformations. If I find something out in one domain, then it'll be true in another domain as well. So what else do we know about A and A tilde? We know they have the same Jordan form. And we know that the Jordan form, within a Jordan form matrix, it consists of one or more Jordan blocks, and those Jordan blocks can be rearranged on the diagonal without fundamentally changing the matrix's properties. But so A and A tilde have the same Jordan form as each other, and let's let the vector V be an eigenvector of A. So A times V is equal to lambda times V, because V is an eigenvector of A. Now let's look at our similarity transformation that we had. Let's take A tilde and let's multiply it by the transformation of V that got us to this new tilde world. So V becomes PV, and then I'm going to just plug in for A tilde, and A tilde was P inverse, and then that's times PV, and then I acknowledge that this thing here is just the identity matrix, and so when I'm done, that's just equal to PA times V, but A times V is lambda V, and so that's just equal to P times lambda V, but if I want to keep this kind of matrix vector, I'll pull this scalar out front, so that looks like lambda PV. And so if you look at this, which ones are important here? I want to look at this one and this one. And so what we see there, so A and A tilde have the same eigenvalues. So lambda is an eigenvalue of A, and it's an eigenvalue of A tilde. So what this basically says is that this vector PV, and it is a vector, this is an n by 1 thing, and this is an n by n thing, so this whole thing is an n by 1 vector. PV is an eigenvector of A tilde if V is an eigenvector of A. So this sort of relates, so two similar matrices have the same eigenvalues as each other. They don't have the same eigenvectors, but their eigenvectors can easily be found relative to each other through the similarity transformation, which here we used as P. So we now know how to find the general solution for a state space equation, and we know that the general solution of the state space equation, it can very easily be related through a similarity transformation to the solution for the equivalent state space equation where we've converted into Jordan form. And we know from a previous video that the Jordan form version of e to the at can very easily be solved for. So we can now